Okay, I guess I'll get started in a moment. Can anyone hear me? Hello, Mike. It's probably quite a long lag, so if you could just let me know if the audio is all right, and then I'll get started. Not very used to the streaming thing yet, so who knows if this is going to work. My poor laptop is struggling horrendously with all of the wires and things. Sorry, I'm having some tea at the same time. Probably sounds gross. All right, okay, I'm just going to start. Oh, it just said the audio bitrate is lower than the recommended bitrate. I'm just going to ignore that. I'm going to stop looking. So I probably won't be able to concentrate on the chat and everything else at the same time. So I'll try and pop back into the chat periodically. Hello, Eric Brombaus here, who has taught me a lot about STM. So that's cool. And Mike, obviously, thank you everybody for your support on Twitter. And we will see how this goes. Okay, so today we're going to be doing, we're going to be sort of bringing this up from nothing. Well, I think I'll leave it in the case. This is the version I wrote yesterday. It's a little Gaussian blob on the 8x8 LED matrix. So I can change its X and its Y. And I doubt any of you will be able to survive as long, but I may go all the way to actually making some simple DSP on this as well, because it does actually work staggeringly for a design that I sort of sketched out really quickly. So I've got a Gaussian blob here on an 8x display. I've got 3 knobs. So the idea of this module is, well, what does it do? I'm going to check that no one's complaining. Okay, it says it sounds fine. This is really just a sort of simple test bed module. I had an idea one evening and I was like, oh, I should just put together some of the elements I've been playing with. And they actually make good learning elements. Pretty much every module with a processor would want this. So you've got like 3 knobs, you've got a little display, you've got an encoder with a button. I can actually invert the display with the click. And I think you won't be able to see it, but as I twist it, I can select a pixel. It's high tech. So the encoder works. The idea is I've got 3 CV, A, B, and C, which correspond to these 3, although they're not electrically connected. They're sort of like separate ADC channels, so that the software can decide if they're a scale or an offset or whatever. So 3 CV inputs, a mono audio input, and then stereo AC coupled codec out. And in fact, the top 2 jacks are actually both connected as stereo and as ADC. So the STM sees it as a CV DC coupled, and then the codec sees it as audio. So you can actually do stereo in, stereo out, or mono in, stereo out. This is what it looks like when it came back from JLC, which is pretty cool. Very simple design. The components go on the back. Classic kind of 2-layer design. I won't cover it in any detail. There are a few mistakes. Let me just point at the other ingredients. Hang on, let me just bring up the schematic. Okay, I'll double check the chat as well because I'm nervous. Check. Keeps getting up desert by high res display. Yeah, I've been using an OLED display, an ITC, for a while, and honestly, I don't particularly like it. So I saw one of those in my drawer, and the entire point of this module was, oh, I'm gonna do something with this. So, oh yeah, I've got in the Switch streaming program, I've got to switch my desktop, haven't I? Dope. Right. Okay. So this is the schematic. It's a STM in the middle. I'm not going to cover this in any detail, but these are the 4 jack inputs, all of which go through the same kind of inverting op-amp configuration to get it down to 0 to 3 volts, classic MCP 604 clamped output full swing 0 to 3.3 volts. And then in addition, analog in 1 and 2 are also put to a little divider and an AC coupling that then goes into the line in. Actually, I do have a drain, so I can drain the, I wonder if that's on the wrong side of the capacitor. It's not a polarized capacitor, I suppose. Is that the right side to put the? Yeah, I think that's right. So there's a little filter cap and a thing to drain away any offset voltage, and then it goes into the codec, which is just the codec that I believe was in the original iPod, and JLC stock it. So it's a horrible little thing, but it works. And then for output, I just AC coupled output from the codec, so I don't have any DC coupled outputs on this device. And then in terms of the layout, I did a 4-layer layout, which is really gross, and I made a minimum of 3 mistakes. So one mistake was that the 16-pin eurorack header I didn't completely center, and I totally could have. And as a result, it very slightly overhangs the board. In fact, I can show that on the overhead view. So if I just switch back to the overhead, check the chat. So if I show you, there's a board, and I actually have a power thing unsoldered. So if I stick this into the power, stupidly, it's not quite centered, so it overhangs by about 50 mil. It's very little, but it's enough to be annoying. So that pissed me off. That was mistake number 1. Mistake number 2 was, here's the cute LED display this is from Adafruit. I ordered it originally, and I left it in a drawer for about a year, and I've just found it. So when I did the footprint, and I'll put the Gerbers and the KiCad files up on GitHub, probably just fire an abandonware, because this isn't wonderful or anything, but it may be interesting for people to see the files that I used to produce this exact PCB with all the mistakes. So so you can see I made a footprint of 8x8 LEDs, and those LEDs are actually in the right places, but I assumed that the pins go all the way sort of symmetrically 8x8. Turns out, no, they don't. The pins are actually narrower. I don't know if you can see this if I put it that way. The pins are actually narrower than, they're not square, basically. But luckily, you can just bend them. And so on the actual piece, because it stands off the PCB sufficiently, I got away with it. So that was mistake number 2. And then mistake number 3, idiot. If I go back to the both cams view, I've seen the schematic. So we have the codec is configured over I2C, the I2C bus, and I didn't put any pull-ups. And you can put pull-ups in the chip, but they're too weak. They're only like 20K, whereas for I2C you probably want 2 to 5K, sometimes even less. So basically it's really soggy if you use the in-chip pull-ups, so you have to go slowly. But I looked at the data sheet, turns out it doesn't care how slow you go. So I'm going to bit bang the I2C on this stream, and it works, so thank God. So I got away without the pull-ups, which was a bit silly. I could probably use the peripheral, although I haven't tried, and I've not enjoyed using the peripheral on the STM of I2C. So I decided that this time I would just bit bang it by hand, because we only use the I2C bus to configure the thing on boot, and then we ignore it after that. So it's not very painful to do it slowly. Okay, I will double check the chat, and then we're going to go into coding. Everyone seems happy. So like I said last time, probably this is going to go horribly wrong and I won't get anything done that I wanted to get done, but we'll see how we do. The other ingredient that I love, and again, I'm not getting any kickbacks, is digital and analog discovery. We may be using this later. So this thing comes with a load of plugins. It's just a 100 megahertz scope over USB. And it comes with like standard, you can see in the little picture-in-picture down the bottom. It comes with a scope adapter, but just go big. Hello. This, which is made by James Carruthers, yes, on Twitter. He gave me one of these. We met him for coffee in real life, and he gave me one of these. It's a eurorack adapter, which connects a bunch of digital in out triggers, but also the 2 waveform generators and the 2 scope input. So you can basically use this as a dual function generator, like an LFO or a non-LFO, HFO, and it just slots in there. I soldered this myself, an Osh Park board, I suspect, which he gave me, and it literally just connects. It just breaks out 2 inputs, 2 outputs, and then a bunch of triggers in and out, which is insanely handy. So we could be using that later. It's very handy. Right, double check chat again. I'll just check making sense so far. have a cup of tea. I might do sort of periodic Q&A just for my own sanity because I'm a bit tired today. I don't know why. And so I may just for my own sort of breaks periodically may just come to the chat if any of you are still there. I appreciate anyone chatting back to me because I'm new to this. And I'll archive it on YouTube and I'll put all of the design files online as well. Right, the other ingredient we need is an STM Nucleo. So I'm going to switch back to the desktop view. So that was the analog discovery, which I highly recommend. So the software we're going to be using today is called STM32 Cube IDE, and it's an Eclipse-based monstrosity. Now, when I first looked at it, I actually thought it was really cool. It had a full IDE, had a full debugger coming from Teensy. It was refreshing. Unfortunately, it's quite buggy, and I'm not going to enumerate all the bugs I've had, but basically it is just buggy as hell. And the IDE itself is buggy, and then the software which they have, which is called the HAL, hardware abstraction layer, is buggy. And I've actually hit a bug in bringing up this board, which has been the case for every single board I've brought up, and it's not like I'm doing anything complicated with these things. So I'm super unimpressed. And the frustrating thing is that, like, if you go onto the STM forums, which is about the only place you can get answers, there's layers upon layers upon layers of Cretaceous kind of layers of old. They didn't always use the HAL software library. They used older libraries. So half of the stuff you find online is for outdated stuff. And then all of the sort of greybeard, brilliant forum people on STM who reply all hate Cube and all hate the IDE and all hate the HAL. So it's not for them. They can't offer advice around it. They just say use the registers on the chip, which is fair enough. But it means that as a beginner, you're just kind of stuck between buggy code and the greybeards hating it. And I feel really sorry for the development team who are working on the STM Cube IDE because it's a good idea in principle, but it's sort of toxic. Everyone hates it. Everyone hates the HAL. And ST have epic amounts of documentation for their chips, but it's also verbose and it's not sort of synthesized into a useful way. So I was hoping that this stream, in a way, if you're new to STM and you're trying to make eurorack, I might be able to cut through a bunch of the decisions, and that's really the intention of this probably long-winded and slightly boring stream. So we're going to be using that software. The other thing you'll want to know is if you want to look up the documentation, type into Google. The best way is to type into Google STM32 chip number, first digit, so F4, family, and then 4, which is what I'm using, a 405. Then you type in HAL documentation. That gets you to a PDF, 1,800 page long PDF. So you have the HAL documentation, you have the data sheet, you have the user manual, you have the technical reference, and then you have the application notes. And each of those are, and the application notes, there are hundreds of them. And it's just a complete nightmare to wade your way through all the documentation. And my internet is utterly struggling, I guess, because I'm streaming. So this 1,000 page PDF that's currently loading is I'm maybe not going to. Actually, have I got this open in another window? I might even have this open in another window. No, I don't. So yeah, you get this giant PDF of documentation hell. But now we're actually going to start building. I've got a little video to play, which is me soldering a bare board. So the first thing I put on is a 16-pin programming header, which I'm going to talk about in a moment. And the SMD stuff was done in China by JLC for ridiculously cheap amount of money. Look at the flux-stained table, horrifying. So all I had to do was stick on the through-hole things. I didn't have a straight power header, so I put in a right-angle one. Luckily, it fitted. And lockdown pane. This was all done using stock stuff I had in my cupboard, basically. And put on the it doesn't freeze the last page. Well, put on all of the lovely pins, and then you get a delightful. Let's roll that again, just while I chat. So the programming header, first thing you need to know is how to program an STM chip. And when they arrive from the factory, they have this ROM on them. That means that they'll actually flash over a variety of different things, even USB serial ports. So you can hook up various pins. But I like to use the full SWD programming pins and use a programmer. Now you can buy a programmer from ST called an ST-Link. I believe there are knockoff ones as well. But I am going to use a wave one in the camera. Maybe I'll do the overhead. So this is a Nucleo board, and I'm going to switch to the going to switch to a schematic view now because it's going to be clearer. So that's a nucleo. And the funny thing is the top half, right, is I've actually got a doodling app here, but I'm never going to remember to use it. The top half is a standalone programmer. So the amazing thing is this whole board is 20 quid or less, and you get like an STM chip for you to like fiddle around with and prototype on. And then on the top half, you get a programmer which can either program the thing on the bottom or can program a remote board. So if you look in my overhead camera in the corner here, I have one of these, and I've built a little adapter that connects. Now, this SWD header here has 6 pins on it. Ground, power, which confusingly goes from your board to the nucleo, not the other way around. So it doesn't power your board, which is super annoying. You have to power your board yourself, which I'm doing from this Erica Synth Pico case. So I've got power going into my module. This is the module here. Oh, it's slipped out of camera a little bit. Let's move this a bit. I wonder if I can do some live OBSing. Let me see. That's a bit better. So I've got the module in my Pico case. I've got the programming cable going to the nucleo, and I've got power. So you've got this standalone ST-Link programmer, and it has these stupid 6 pins, which is 3 volt 3 going from your design to it, ground, SWO, which you don't need, and then data and clock, basically. Now, those pins are kind of annoying. Oh, and then it also has a separate 2-pin header that's slightly offset and not on a grid, thanks ST, for a UART to transmit and receive for like serial. So you can do like you can use PuTTY to connect and send strings of text to and from your board. So I built a little tiny adapter. I don't know if I can bring it up to the camera. Let's go to the overhead. I'm not very good at this, sorry. Overhead cam. So I've built this little tiny hat that sits on top of those 2 connectors and also has a flying lead for power, so that if I have a stray 3.3 volts lying around, I can jam 3.3 volts. And I've basically routed the both connectors over this little cable. And at Eric's suggestion, I actually used the pinout of something that I used a pinout that ST used called the STDC14 pinout. You can Google it, just because it's on their latest ST-Link programmer that I don't own. But I thought, well, it's a really cute small, it's like a half size. That looks like a eurorack thing, but it's basically double density. So it's actually really tiny. So I'm able to use that as a programmer. So ingredients. You get your boards from JLC that you've ordered, and they arrive and they're assembled, and you stick all the 3-hole components on. You whack a little programmer on, which is surface mount, slightly annoying to solder. Whack one of these in, or if you want to, you can do bodge wires. You only need 3 or 4 bodge wires. Oh, you need reset as well. There's a reset pin, data clock, and ground. And then you just bodge them onto your nucleo programmer or your ST-Link programmer, and you're away. So then we can start doing software. That's it for the hardware intro. I'm going to take 5 minutes to look at the chat and drink some tea, and then we're going to just go into like typing. I've still got pink doodles on the screen. I'm going to bin that off. Clear screen. I don't think this doodling program is going to help me. Right, let's see how everyone is doing on the chat. Eclipse, I do not enjoy proprietary IDs. I guess power on the program is separate, so there's less risk of frying both. Yeah, that makes sense. There's actually a header, there's a 2-pin header. So let's go and look at the nucleo. So as I say, the power goes in from your board, but conveniently this little header here seems to have 3.3 volts on it sitting there. So that's what my flying green wire attaches to. So I jack that power out from, this is powered by USB. So USB comes in, gets regulated. Totally, it's only meant to power this, but if you're running a small enough board, you can basically sneak a bit of power out of there and jam it into here and send it off to your board, which is what I do sometimes. Now I'm powering off eurorack like a good boy because I have analog bits. Okay, let's do file new project. I think it is time. It is time for file new project. It is time for new project. Right. My God, 20 minutes already. Fuck it, let's do it. Here we are, this horrifying program. Oh, I'm not even put it on the right desktop. Come on, Evans. This is STM32, and these are all of the various things I've brought up on this laptop, which are basically, like there are so many bugs. So for a long time, for example, it would generate mistakes where it wouldn't generate the DMA initialization in the right order. So your DMA silently wouldn't work. And it's just like, oh, are you for real? And then it wouldn't open old projects. Every now and then they upgrade it and then it won't load old projects. It wouldn't load a project for my Mac. It would just hang forever. So I ended up just creating new ones. And sometimes mysteriously stuff would just stop working. So I just do file new project a lot. So you can kind of see these projects. This one was Plinky at one point and it just turned into, oh my God, what the fuck? Because I was up to Plinky 9, I think. Not actual physical Plinky 9, just like within this stupid piece of software that is unfortunately the best way to get up and running. And I should say also that I've noticed a bunch of people who've got Visual Studio Code working. So my workflow is that I use this program. I think STM Cube, despite all my bitching, is by far the best program for bringing up a project, which is what we're about to do on the stream. I think once you're into the sort of meat of software development, you want to do it in an emulator on PC with a familiar environment, or you want to use something like Visual Studio Code, which I haven't taken the time to figure out. But this thing generates make files, so it's actually very easy to just get Visual Studio Code to just build your make file for you. And they have a really good integrated debugger there as well. And I believe there's an ARM Cortex-M4 debugger plugin for Visual Studio Code. So if I had to do this for a day job, that's what I'd be pursuing. But because I don't, I basically bring up the boards in this thing, program in an emulator, and then drop the DSP code back into here. So what we're going to do, file, new, oh, for God's sake, I'm not very good at using a mouse, STM32 project. And this thing downloads like 900 megabytes of, it's just so slow, it's unbelievable. Come on. Okay. It's also opening things on the wrong page just to mess with you. So this is actually quite useful. If you're using a Nucleo board, you can just go in here and you can be like Nucleo, and all of the different Nucleos they sell, you can just pick it from here and it will make a project for you configured for that board. But we're not going to do that. We're going to do look, now it won't let me do a part number search. Are you for real? Right. STM32 F405. I believe it's an RG. Ooh, good question. I think it's an RG. Let's just, no, that's LQFP64. Okay, the picture's misleading. Yeah, so that's our chip. So we want that one, and the OK button is off the bottom of the screen. I mean, of course it is. So believe me that I'm clicking next. And we create a name, so we'll call this Wagyu2. Don't use C++, it's just extra nightmare, more bugs. They don't test it, even less. You get to choose what firmware you want, which it downloads. It takes like 900 gigabytes of download. And it creates this device configuration tool, which is actually really handy. I have a hard time understanding how to program the ST Nucleo though. Yeah, so program the Nucleo itself. So basically, if you've got a Nucleo, all you need to do is plug in a USB cable, go into STM32 Cube ID, as I'm doing now, go to the board selector and select the Nucleo board, and everything should just work. It may complain about firmware updating, so you need to firmware update. It does work. If you want to program your own board, you basically move a couple of jumpers, which allows it to program external things, and then you run the wires over to your chip. So here we have a blank project, completely blank STM32 project. I'm just going to go back to the don't use C++ bold. Don't use C++ anyway. It's a shitty programming language. And don't use C++ in STM Cube IDE because, I've recently moved to using C for this hobby stuff, and I absolutely love it, and I do not miss C++ at all. Anyway, that's a different topic. So the nice thing in here is that basically you get a picture of your chip, and they tell you if you left click on any button, they'll tell you all the different functions. Every pin on STM. Let me see. I have an ST-Link 2. Don't have many connect-driven cables. Have you had an experience using Arduino IDE? It feels like a much more polished environment. No, I've used Arduino IDE for Teensy, And I'm not sure if you're saying that Arduino is more polished or this is more polished. I actually prefer this to the Arduino one. I also hated Arduino and I switched to Makefiles. The main reason was that it's slow, also like this, but it also doesn't have a debugger. And I actually find having a debugger really helpful. So I find this better than Arduino, but I guess it's all about taste. And again, with Arduino or Teensy, I rapidly moved away from that environment because it's just horrible to type in. Right, so what I like about this is that for every chip, you can basically find out that this pin, PA0, can do ADC inputs, it can do timers, it can do UARTs, it can do USART. So when I was actually designing the schematic here, I actually, chose, I had an instance of CubeID open, and I basically set things up. So I know that PB6 and 7, pin 58 and 59, I decided were going to be a UART. So let's just bung them in. So basically I'm saying I want those pins to be the UART. 50 what? 58 and 59? Right, I want those to be UART. USART 1. I vaguely remember it being USART 2 on the other one. Oh, well, I don't know. Anyway, so then you go over to connectivity, and was it USART 1? It was USART 1. You say, I would like USART 1, and we will have asynchronous. That just means 2-wire UART. Done. Don't bother setting any parameters. And they go green, meaning, okay, those wires are now configured. And basically what we're using here is a glorified code generator. So if I hit save, actually I'm not going to hit save quite yet, but we'll hit save in a moment. The other thing we should set up is the clock. So over here on the system core, other thing you need to just do what I'm doing basically. This is learned from, so debug, we want serial wire debugging, which is basically what allows us to debug it over the via the Nucleo board or the ST-Link programmer. And serial wire basically means you've hooked up N reset, SWD, basically SWD pins. Where have they gone? These ones. You've hooked up STWIO, you've hooked up SWD CLUC, SWO doesn't matter, not connected doesn't matter, reset does matter, ground does matter, VCC doesn't matter, or maybe it does. I don't know, chuck VCC on there anyway. So yeah, so you've hooked that up, and then choosing serial wire in sys under debug is what allows you to configure that. Done. Now we're going to do clock. So you don't actually have to have any clocks on most STM chips, or you can have a high-speed clock or a low-speed clock or both. We're going to have a crystal on our high-speed pins. So now these two pins have gone green. And if we go and look in my design, indeed, pins 5 and 6, I hooked a crystal to, and I actually hooked a 16 megahertz crystal. So pins 5 and 6 are now configured for a crystal. So I go to clock configuration, and this nightmarish screen allows you to set up how fast the chip runs. And you say, crucially, how fast your crystal is. So the only sense of time this thing has is basically what number you fill in here. So I'm basically promising to the software that I'm going to feed it 16 megahertz on the way in. And if you don't have anything plugged in there, it can use its internal oscillator. But if you're doing something like USB or audio, where you want precise timing, you probably want some kind of circuit that does precise timing. So I've whacked a crystal oscillator on there. And then we could feed, you basically want to just follow the money. So let's make this divide by 8 maybe. What we're aiming for is that the chip can go at a maximum speed of 168, I think. So let's just dial in 168. Oh God, you see, look, buggy. Oh, please, mum. Right, I can't convey to you on stream how unusable this UI is, but it's sort of glitchy and shitty. 168, yes, I clicked it. It doesn't look happy over here. Let's divide this down. 84 is still too fast. 42, that'll do. And 84 is maximum. Hey, everything's gone green. And that's a clock safety thing. It'll fall back to the internal oscillator, I think, if it finds if your crystal blows up. So everything's not red now. So I've basically managed to configure that I have a 16 megahertz crystal, and sysclock in the middle here is 168, and hclock is 168, which is as fast as it can be. And then these other peripherals are all being clocked at reasonable speeds. Good, save. So what it does now is it generates code. So basically, if we go and look, all of this UI stuff is purely to generate the following horrible looking code. It generates a main.c. It generates startup, some interrupt handlers, some wrappers, and a makefile. And basically gives you these markers where it says user code begin, end, and you have to put your stuff in between these markers. Otherwise, it nukes it next time it generates stuff. So all it's done is it's created the UART that I asked for, and it's created the GPIO. Let's actually get the UART going. So I didn't do this yesterday, but I'm going to do it today. I am surprised because, okay, sorry, this is where I do start doing coding. So the first thing we need is some header files because it's C. I'm going to bring in those four because actually it's a chat. I'm going to have a word with the chat. How's it going? Bloody hell, seems like a nice C function that you can pass. This is not doing a great job of selling me on STM32 IDE. Yeah, as I said, it must be horrible for the team who are developing it because I think they're valiantly trying to do a good job. And I actually think it is the best way of bringing up a chip from nothing. I mean, what's cool is I can bring up any of their chips of which there's a bewildering number. And rather than leafing through a data sheet for tables after tables after tables of like what you can and can't do with each pin, I can actually point at it and, the clock configuration I'm not going to look at again. I'm going to basically just be staring at this and going, right, I want these pins to do these things. And you get into a rhythm where it's actually incredibly helpful. And for some of the peripherals, you'll see there's a bunch of parameters. It's actually really helpful to be able to generate them. So although I bitch about it, and it's not the greatest thing to code on, the fact that they've basically tabulated all of their bizarre hardware restrictions into a UI is laudable and is really good. Reliable clock speeds are also fancy compared to Arduino. Getting more interested. Bloody hell, seems like a nice C function that you can pass a bunch of parameters to would be a lot nicer to work with. The ID is well over top. Yes, I agree with you. But I did find it as a nice way in to the setup. Right. Also, I'm not used to using it at 1080p, which is what I'm streaming at. So it's a little better when you have a higher resolution screen or a bigger monitor. We were going to get the UART working, weren't we? So we go back to main.c. Actually, oh God, I've got all my old fold. Let me just close down some of this stuff. So this is basically, it remembers all your windows, one of those jobbies, right? Look at this, look at the update rate. Java, man. It's like classy. Yeah, I've got all the old main.c's from my old projects. Let's just nuke them all before I reveal to you all the source code of my other projects with their full horror. Blah, blah, blah. Also, every time you break in the debugger, it opens up a random, they do ship source for all of their libraries, which is nice. Okay, all right, we've closed everything down. So we've put the headers in. So another thing I'm just going to quickly crib from my sort of off-screen thing is find a nice spot. Private user code. This feels fairly private. This is just a little debug log. So it's like printf, takes a format string, turns it into a little 256 character buffer, and then calls this HAL function. So this is the first example of their lovely HAL library. So HAL is their hardware abstraction layer. The idea is that each chip actually has slightly different hardware. So they may change the registers underneath, and you can directly access the registers. So in fact, later on, we're going to be accessing the GPIO pins. And so GPIO port B is that, and it has a bunch of, look, autocomplete, has a bunch of fields, and these are actually memory maps. So if I write to output data register, I can literally set 16 pins at once by doing that. So 16 pins have just been set. So that's the low-level way of doing it. Or you use HAL, which basically abstracts it and gives you help. So it sends amount of data blockingly over the UART. So we're going to use this now to say hello world. It's never going to work. HAL init, blah, blah, blah. And then this is a bit like Arduino. You have an init. This is basically setup from Arduino land, and this is I can't remember what it's called in Arduino land, but then loop forever doing something. So let's just do debug log hello world, because of course you have to do carriage return line feeds for my version of PuTTY. I don't know. Hit compile. While it's compiling, I'm going to bring up PuTTY. Everyone knows PuTTY, right? Also known as Telnet. Oh, come on. My computer is really not, it's a little laptop and it's not very happy. So basically the ST-Link shows up on your USB port as a COM port. So I'm just going to connect to COM port 3, which I happen to know this is. And we're going to debug our program for the first time. Oh, for the first time it asks you, do you want to debug it? And I do. And you wait, and it's connecting to our little thing. And it's now this is a wonderful moment in the bring up of a board. Now I'm glossing over this, but what we just did, we wrote some code, we configured a chip, we pressed debug, and it actually connected to the chip, flashed it, downloaded the code over USB, and then opened up a C debugger sitting on the first line, and we can actually step over this code and set breakpoints. So for example, I can set a breakpoint on there. I can hit play. We're on our debug log hello world. We can bring up our putty window, and that was actually as it rebooted, it managed to run and say hello world. And if I step over this line, it will say it again. So hooray, that is our little module down here talking over this thin grey wire to the ST-Link, which is then talking over USB to my computer, which is turning into a TTY in there. So basically, we now have debug TTY in. Next peripheral. And we basically just go through the peripherals and knock them down. So it's taken me 36 minutes to get this far. I would love to get all the way to audio. It may be a long stream. I don't care. If you guys all need to leave, I forgive you already. If you have not already left, I'll put this on YouTube. But I'm tempted to just keep going until I get too exhausted, or something goes horribly wrong, it goes up in smoke, and you get to see the magic smoke come out. Blah, blah, blah. Holy hell, that was fast compared to Arduino. Yeah. Yeah, SAMD, I haven't tried SAMD, so I have no opinion. I'm going to address the paste your code here thing as well. Yeah, SAMD I haven't tried. The reason I went SCM was because it seemed to be used in loads of modules. And should I switch this light on? Is that going to improve the picture? It's getting dark. I don't know if that improves things or not. I think I might switch it off again. I don't know. Who knows? Yeah, I just use SCM, and I'm enjoying it. I like it, and they have some fat chips as well, like the H7. At the time, I needed for Plinky I wanted 2 independent full duplex I2S things, and I think that the SAMD I was looking at had 3 half duplex ones. I needed effectively 4 half duplex ones. Anyway, that was ancient history. That was an accident. So I have nothing against SAMD, but this is the STM world. Okay, so let's do some GPIO action. We've got some LEDs on the front here, and let's light an LED. So we go and look in my thing, and I have pins 8, 9, 10, 11. I labeled them as, so the matrix, LED matrix, is basically a classic matrix rows and columns, right? And for some reason, the pinouts are bizarre. They go in these crazy orders, like 1, 2, 3, 4, 1, 2, 3, 4. Sort of, I think it's designed so that if you rotate it 180 degrees, it doesn't get back to front. And I didn't actually read the datasheet right, so I labeled these positive and negative instead of anode and cathode, because I always get anode and cathode confused. So it turns out I still got it wrong, and I got positive backwards. So to make the LED light, you actually need to drive P low and N high, like an idiot. So what I'm going to do is I'm going to set these up, these N's, as GPIO pins, and I'm going to set the P's up as GPIO as well. I'm probably going to do P1 to begin with, and I'll explain why in a moment. So we need to do the ends, which is 8, 9, 10, 11. So we come over to here, 8, 9, 10, 11. Right, there's 8. I want you to be an output. I want you to be an output. I want you to be an output. And you can give these labels, but I'm not going to bother because it's boring watching me type. 8, 9, 10, 11. What else was there? Spot the other ends. 39, 40, 51, and 52. So 39, 40, 51, and 52. 39. So 50 is going to be up here somewhere. So 50, oh, what was it? 51 and 52. Yeah, 51, output. 52, output. 39, what? 39 and 40. 41, output. 39, output. Okay, so that's our ends. So if you go look in the GPIO section, you see that we've listed them all out, and they're all set to low. You can say whether they have pull-ups and pull-downs and all that stuff. I'm going to say that N1, which is 51 PC10, so PC10, I'm going to ask to be high. Right, so 1 pin is going to be high. I'm not even going to write any code yet, so we're going to basically pull that one high. So that's the first column, sort of x equals 0 column. Fine. And let's do P1 to the corresponding pin, which is P1, which is pin 44, PA11. Here it is. I'll set you up to be a GPI output, and you are going to be low, which means it should, if we're lucky, just light up one LED. Should we find out? Hit save. It does code generation. Would it be instructive to look at the code it generates? It's pretty simple. Oh, the MFC point. Yes, it does feel a bit like MFC. And luckily, they've actually put it's slightly nicer than MFC in my ancient memory. So they write routines like GPIO in it, and then they basically say set all the pins low. Classic sort of stuff. Set up the pins. Push pull means it's a not open drain. It's like it can pull it high or low. No pull ups. Low frequency, so it slews quite nice and slow, doesn't generate noise. Then configures it. And you could write that by hand. And experts will tell you that you should write it by hand, but I find it incredibly useful when you're just sort of feeling around to bring up your chip so let's stop debugging, hit compile. It tends to do a rebuild all every time you edit the chip layout, which is slightly annoying, but okay, that's compiled. Debug. There's also a run button, which staggeringly they only added in the most recent update, and I've learned muscle memory not to click it because it didn't exist before. Right, now in theory, if we run this, I may have set up the pins correctly to light one LED. We've still got the breakpoint on Hello World. Oh, is there an LED? It was actually occluded from my view, but it is actually lit. I don't know if you can see that, but indeed there is one LED lit. So on that massive success, right, I've told you how to do LEDs, we can just go home. I shall talk to the chat for a moment. It's all here, yeah. How do you feel about the LED? Eric says he can stay. Well, I'm glad you can say yes, one LED. Okay, brilliant. But an LED is boring. Let's do a row of LEDs, but also let's do PWM. So that's why I didn't bother setting up all the Ps. It was PA11, I believe it was, wasn't it? So now we are going to quickly set them up. So I happen to know, because I designed it this way, that P1, 2, 3, 4, and 5, 6, 7, 8, I chose to be pins which were timers, which had timer capability, if you like. I've got to remember which pins they were, though. P1, 2, 3, 4, they're all over the place. 44, and not 41 to 44. Okay, 41. Oh, God, this is awful in 1080p. 44, yeah, that's 44. So I want that to be timer 1, channel 4, jolly good. Timer 1, channel 3. Timer 1, channel 2. Timer 1, channel 1. So basically, that they've got orange saying I've requested that those pins be used for timer 1, but I haven't actually set up timer 1 up yet. And then the other Ps are 38, 13, 38, and spot the other Ps, 26, 27, sugar, 26, 38, 38 should be timer 3, channel 2, I'll take it, 38, and generally the low number of peripherals are in nice places, and the high number of peripherals start getting like the timer 3 starts getting scattered around on the low pin count chips. So P8 is 38. Who can see? Okay, 26 and 27, which is going to be around here. 26. Timer 3, there you are. 27, timer 3. So we've just got one more timer, 6, 7. You're probably screaming at me. P5, 56. That'll be up high. 56. There it is. Timer 3. Okay, so we've set up our 8 pins for the rows. Rows or columns, whichever round it is. So now we go to the timer section. Timer 1. And we say, right, we want to be clocked by the main clock. That'll do. And no, we want to set them up as, and you can set up, they're incredible, these timers. You can do anything with them. You can measure pulses, you can make pulses. But we want PWM, boring. So we're going to generate PWM 3 for 4 channels of PWM. And we're not going to pre-scale it, and we'll set the counter period to like 256. So basically it's going to count to 256 and then go back down to 0. very boring. And everything else I think we can leave as is, yeah, blah, blah. Then timer 3, same deal. So we want a clock source, internal clock, PWM generation 1, PWM generation 2, PWM, and 4. Did I do that right? I hope so. And then counter period 256 and hit save. Now, they will all default to having a, they should all just be PWM, but with a 0 period, which means they're low, which is the right way around to light the LEDs. So we'd expect a row of LEDs to light up, but hopefully spoil it, they won't, because I've made a mistake. But I made this mistake yesterday, so I thought I'd make this mistake with you. So I'm like, yay, I've got my one column pin is high, configured in GPIO, which is the first column. And I've now made all of the rows, which are going to be PWM controlled for brightness, all be 0. So they should light the first 8 LEDs. Quiz, why won't they light? Why will I be disappointed when I hit this debug button? Hit play. And we should see absolutely no LEDs. And if we break into it, we just see that we're in the while loop, but there are no LEDs lit. And we're like, oh, that's so sad. Why does God hate me? Let me see if the chat guessed. Well, I'll put you out of your suspense. This is a super exciting stream, 45 minutes of, I think this is going to be 2 hours, guys. But yeah, again, we'll see. So the answer is you have to start the timer. So the cube ID will generate the code to configure the timer, but it won't start it for you. It doesn't make an assumption about when you actually want to start the thing. So oink, we are going to start the thing by finding a nice early point in the code to start. Let's go for after we said hello world. Now, hilariously, there is a Tim channel all define, and these are actually defined as bit masks. So I tried using Tim channel all, and it didn't work. And that's just the experience of using their crappy HAL libraries. Like, it's not particularly well documented, and I was like, fuck it, life's too short. Let's try this. So gross as it is, I just start all 4 channels across the 2 timers that we did, and we hit run. Why did I choose 1 and 3, by the way? That's because where the pins fell naturally when I was doing the layout. So it's kind of a back and forth between the software and the hardware and the restrictions. So if we hit play, if we're lucky, we get a row of LEDs. Do we get a row of LEDs? I think we get a row of LEDs. And breathe. Yes, enable the timer. Mike Ball got it. Winner, Mike Ball. Give yourself a pat on the back. Has it hit in the stream yet? Yeah, the little LEDs are there. I'll just have a little moment of observing them close up because it's like, yay. You know what I'm going to do? I'm going to move this down. Since we're focusing on I have no idea how to crop in OBS. Oh, shit. But I do know how to make things bigger. Embiggen. There we go. We can see our LEDs a little bit better. Right. Oh, stretch. We're doing well. Now let's do, we've got to cycle the end pins, right? So I'm going to write this as a little state machine. Are you getting excited? Let's cycle the let's write a little routine called update LEDs, and its job is to update the LEDs 1 row at a time, right? We're multiplexing. So I'm afraid I'm going to just sort of accelerate a little bit by doing the here's one I made earlier kind of vibe. So I'm going to give myself a little 8x8 VRAM buffer, which is going to be our grayscale picture that we're going to display on 8x8 pins. We're going to have Y pins, which are configured as like, now I didn't lay them out. I laid them out to make the traces short, not to make my coding life easy, which is the right way to do it. So 4, 3, 2, 1, reasonably sensible, and then 1, 4, 3, 2, not particularly sensible. And the X pins even more lunacy, 10, 9, 8, 11, 3, 2, 1, 0. I just did that by tracing out from the schematic to the pins, and it's just annoying, but that's how it is. And then here's a little tiny routine. It has a tiny bit of state, which is X, and it just cycles around. And we're going to call right pin, and we're going to clear the N pin, the last N pin, the old N pin. So at this point, X is like we're clearing out we're unilluminating the last row. We're moving to the next row, and then we're setting the and finding this macro, by the way, is a case of Googling. But there you go, spoiler, that's how you set the PWM frequency, compare value, sorry. And if it's 4 and higher, we use timer 3, otherwise we use timer 1. That's which timer we want to set, and that's the color from 0 to 255. And then we, having set the 8 timers, we illuminate the thing. Right, let's call this in our main loop. So update LEDs and then sleep. Bargain. There's not much in our VRAM. In fact, our VRAM is full of zeros, which is fully bright, so the entire display should illuminate. So we're making rocking progress. And we will hit play. Shall I try the run button? I've never tried the run button before. Let's try the run button. I don't know how you stop it running. It's connecting the debugger. What's it doing? Shutting down. Debugger connection lost. Oh, well, it ran. Oh, I see, it debugs and then disconnects. Well, that's a bit simple, but fair enough, it worked. And look, everybody, we have a complete grid of LEDs with a little bit of strobing because it's taking 8 milliseconds to cycle that. Now, I'm also going to introduce you to an alternative way of doing this timing, which is that you can also get rid of this. And in the interrupts thing, there's a thing called systic, and it's basically a callback every millisecond. And so if you wanted to, we could call update LEDs. We don't need the delay because this happens every millisecond anyway. We might need to forward declare update LEDs like that. Compile. And I'll just prove that it works, and then, well, we'll leave it in for a bit. We'll leave it like this. This is nicer because it means just you can do your UI update in here. Now, the reason I'm hedging my bets is actually because the plan is I'm going to put all my audio DSP in an interrupt handler as well. So basically the DMA is going to happen for the audio every 64 samples or so. And it's going to be like, more audio. And I'm going to do a bunch of work. Excuse me, I've got hiccups. I'm going to do a bunch of work that takes long enough that it actually starts making the systic handler be a bit wobbly. And it beats against the systic handler as that happens. I've been here. So basically, I realized that the DMA callback for audio is absolutely rock solid, right? Because it's every 64 samples. So it actually serves as a better low frequency clock. In fact, 64 samples is like 1.5 milliseconds to 2 milliseconds, depending on your sample rate. So systic handler for now, while we have no audio, but I'm actually going to move this into the audio callback. But fundamentally, you can do sort of, do your UI here, read your buttons, regular, nice and regular, like. Did we test this? I don't know if we did test this. Let's test it. Screen should still be white. Waiting for debugger connection. Oh, I hit the debugger that time. Muscle memory. Top tip. When you hit wait for debugger, you have to wait for it to come up with a screen pointing at HAL in it. Because if you click it too fast, it gets confused, and sometimes you have to power cycle the Nucleo. It's just super lame. So you just have to learn the muscle memory to wait. And that's, again, it's a little shonky, but it's still cool. And behold, we have our multiplex display. And if we could go into high speed mode, you'd see that was just sweeping across. Okay, let's fill VRAM with something. Let's do pots. Let's read the pots and then use the pots to display something on the display, because that would be cool. Pots. And talk to chat because I'm tired. How long from getting an LED to come on to getting an 8-band spectrum analyzed dance to this tune? I think we could do that in this stream, but I'm not planning to do that. But yes, that would probably be an hour or so. If higher than 4, use timer 3, not timer 1. What was all that about? So where was it? It was an update LEDs. So if you remember, if the in the pinout, I configured, you only get 4 channels of PWM per timer. So a timer is like a little bit of hardware in the chip that starts ticking, and I told it to tick, clocked at 168 megahertz and count to 256, and then back again, count to 256, and then back again. And then it has 4 channels where it can generate a PWM square wave, but only 4, and I need 8 for my 8x8 display. So I did the same thing for timer 1, 4 channels, and then timer 3, 4 channels. So for y equals 0, 1, 2, and 3, I want to configure timer 1. And for y 4, 5, 6, 7, I want to configure timer 3. And then the channel that I want to configure is 4, 3, 2, 1, 1, So these four, this is timer 4. My mouse just died. Channel 4, timer 1, channel 3, timer 1, channel 2, timer 1, channel 1, timer 1, channel 1, timer 3, channel 4, timer 3, channel blah, 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 3, and so on. And then this is the PWM value, right, the brightness. So this basically says, waggle your pin according to the amount written into the VRAM at this coordinate, and it configures all 8 kind of timers, if you like, and then meanwhile the other side of the LED is off. And then on this line we say, right, turn on a whole row, and so a whole row of LEDs. In fact, I could do something like static int slow equals 0, slow plus plus. If slow is less than 100 milliseconds, yeah, return, so do nothing, and then reset slow. So basically that's basically our state machine is now going to just ignore every 100 ticks, or only run at 100th rate, so we can actually watch it cycle. So we're configuring all 8 timers instantaneously, but we're cycling the rows. So I've basically made the multiplexing go super slow. So now we have a little scrolling, should have a little scrolling line pattern, which indeed we do. Hooray! Oh, by the way, just a aside, I change of pace for a moment. OBS, oh fucking BS, there you are. Overhead. So when I ordered this, I didn't know, I talked to LPZW modules about this, and I was like, should I have a completely open square? It's a bit retro. Should I do a grill of holes, or shall I do a basically no solder mask on either side, no holes? And in the end, I decided to try both. So I didn't do the open hole completely. I just did 2 out of 3. And it's really funny. JLC actually wrote to me and went, "You've got a bug in your Gerbers. You forgot to drill holes in the left side of your board." And I'm like, no, that's they're really good. It was cool. They emailed me and basically said, "Do you want us to fix your board for you and drill holes on both sides?" And I was like, "No, that's the only difference between the 2 sides." Anyway, you can't see it, but I tried it, and it's basically way too diffusing. It's better than that, but if you put it right up against it, it was spreading the thing too much. Basically, the light bounces around too much inside the fiberglass. So alas, I had to go with holes. But the holes look cool. So it's not as bright in real life, by the way, as it looks like it is on camera. It's like, it's not so bad. Is everyone enjoying this? We've done almost an hour, so I'm going to celebrate the hour by just stretching. The plan is I'm going to do a recap of what I'm going to cover, because we're actually making pretty good progress now. So I'm going to do the pots next, so that's reading the knobs, and we're going to use that to animate the display. As a side effect, that will also give us CV input just out the box, and we can actually look at that, and we'll use the analog discovery scope to generate inputs, send them in to the CV, and just see that the numbers are waggling around, basically. And that's kind of that will mean that we've done all of the pots, all of the display, all of the CV inputs, and then if I've still got the energy, I'll then go into the audio rate codec stuff, and most of that will just be copy paste of existing code, because it's just basically really verbose stuff. But there's some I2C bit banging stuff, so if people are into that stuff, I might cover that in some detail. I reckon I can fit all of that in all of it into probably 1 more hour. I probably won't get to writing much audio DSP. Maybe I'll do a part 3 stream where I actually do audio development on this thing, having brought it up. I think that might be a sensible place to cut it. So we're not going to be making too many amazing bleeps and bloops. I did actually, I've got a little contact mic here. And if I was going a bit faster, I would have connected the contact mic into the thing, programmed some kind of effect, maybe a reverb or granular delay or something, and then sent that out to the output, which I've got plugged into my PC. But as it happens, I'm a little bit, I think it might be too much for one stream, so I might do that on the next stream. But we've still got plenty to do. We have also got an encoder here. So this is a knob you can twiddle and click. So we'll bring that up as well, which just covers how you do switches, which is pretty simple. All right, back to the grindstone. I've actually got 10 viewers, so thank you 10 people for leaving it on YouTube in the background. Yeah, I agree, do some time for the bloops. I might do that on the next stream. Anyway, let's see how we do. Oh, cracks knuckles, drinks cold tea. Hang on. ADC. Right. So if we go and look at the schematic again, It's pretty simple. There are 3 pots connected across ground and 3 volts, and they just go straight to pot 1, 2, 3, which are up here. And conveniently, the ADC1 gets really nicely numbered pins, A0 through A15, basically, are all analog. So I've got the 4 CV inputs, 2 of which are aliased against the codec, and then the 3 pots. So we've got 7 channels of ADC. So now let's just do 7 channels of ADC. And again, this is where this bad boy really shines. Let me just come out the debugger. Maybe I'll resize this to be a bit bigger. Oh, look at that refresh rate. I mean, seriously. Okay, so PA0, I want that to be an ADC1. The first time I ever did analog to digital on an STM, I just randomly had wired my chip to use ADC3, and I could not make DMA work with ADC3, and it turns out it was a code generation bug in this piece of software. So I now never use ADC3 from pure superstition. I just use ADC1. But it's got 16 channels, so I mean, you know, still pretty good. And we're using 7 of them. So I go to analog, I go to ADC, and you can see that it's basically switched on the first 7 channels for me. Now, there's so much flexibility on the ADC. You can make it, oh, I'm not on the shitting, fuck, I'm not on the view. Thank you, chat. OBS. Fuck. Desktop. Right. Sorry, what you didn't see me clicking there was I was basically going around these 7 pins, going ADC1, ADC1, and basically configuring these 7 pins as ADC. Riveting. And then when I came over to analog, you can see that it's switched on 7 analog things, and now we have a bunch of parameters. And I need to take a moment to say the ADC on this chip is super awesome peripheral. It's capable of basically running by itself, insanely fast. It can sample multiple pins for you in order, in any pattern you like. It can DMA the results out to a buffer. It can even, on some chips, oversample, and only on this chip it doesn't oversample. But you can basically write it to a circular buffer and have it take like n samples. You can change the speed of it, sampling. You can change the accuracy. It's incredibly powerful. So the key settings are: you want scan conversion mode, and what that basically means is you want to scan over a bunch of pins. So we're going to configure 7 pins. We want continuous conversion mode. We do not want continuous conversion mode. So if you do that, it says that when it gets to the end of the 7 pin, just go around and do them again. Keep going and keep going and keep going. And basically, if you've configured DMA, it will DMA the ADC results into a buffer. So a really common way to do eurorack knobs is to switch on continuous conversion mode, give it a tiny circular buffer equal to the number of pins that you want to do, and it will just basically keep them updated. So magically, the array in your C code will just be magically the latest knob value. We're going to almost do that, but I'm going to slow it down because I actually found that indeed that can actually hog the bus a little bit on some of the slower chips. So I'm going to trigger it with a timer. So I don't want to continuously convert. I want to basically trigger you. And you could trigger it from software as well. Discontinuous conversion, I don't want. DMA continuous requests, I don't know if I want that or not. We'll see if it doesn't work. End of conversion or end of all conversions, I tend to put that. So basically that's whether or not it raises an internal flag on each pin or after each set of 7. And then I want to say that there are 7. So I have to click this little button. And I'm going to say regular conversion launched by trigger 2. So I'm basically going to use timer 2 to trigger the ADC. So I can basically say at a certain frequency, sample my inputs. So, you know, if you wanted your inputs to be sampled at 100 hertz or 200 hertz or 5 hertz, whatever, you can do that. So then it shows me the wrong number bug. Look, literally, I just set 7 and it showed me 5. Thanks very much. So channel 0 is correct, but then it defaults them all to be channel 0. So this is basically saying, go through and do 7, and the scroll bars don't update either because I don't know, God hates this or something. Oh, how am I going to channel 2, rank 4 is channel 3, and so basically it's saying you can make it sample in any order you like. So you could be like, do this channel, then that channel, then this other channel, then do channel 0 again. Oh, and actually do you know, skip a bit. And for each of these, you can say how long to dwell on it. And I'm going to actually talk about that. So more hot tidbits from Alex. So 3 cycles is a pretty short sampling time. So the way it works is that basically it switches an internal mux onto that pin, and then it allows a capacitor to charge up. And when you're driving it from an op amp, as we are for the first 4 channels, that's actually fine because the op amp is able to basically just jam it to be the right value. It's quite, powerful. The input impedance is easy to, you can get over it. But our pots are quite floppy. They're like 50K pots. So I tend to make my, I don't know, superstition. I make my pots like have a bit more sampling time because that way there's more time for the charge to balance between the sampling capacitor inside the chip and the pot. So yeah, I make my pots go a little bit slower. So we've configured our ADC channels, and the UI is completely broken and won't let me see the settings anymore. The next thing we need to do is we need to give it DMA. So we just go to DMA, we say add, we want ADC1. This is all good stuff. You want circular. We don't need to bother with FIFO as far as I know, and it's going to DMA 16-bit numbers, half words. So fantastic. So we've basically just set up 7 pins, ADC, circular DMA, triggered by timer 2. So we should probably set up timer 2, but I'm going to hit save. And while that's generating, I shall stretch and look at the okay. Timer 2. Hello, timer 2. We are going to trigger you on the internal clock. We are going to set the period to a bunch. I don't know, 10,000. I think this is clocked at 168 megahertz. So that's 160. That's 16 kilohertz. That's probably too much. There. Should we divide down a bit? I don't know. Divide down a bit. And we are going to say, now this took me ages, you want to say update event, I believe. Now, if I've got that wrong or misremembered it, then we're going to be sat here scratching our head and having a debugging session on our hand. But this basically says, when the trigger happens and you've counted to 10,000, do update event, which I think is a stupidly named enum. That turns into an enum in the code. And basically, I found that out by just reading sample code. But you basically set it to update event, which now we set the ADC to, let's go and look at the code it generated, actually, it might be instructive. So basically, it's calling timer 2 init. The period is 10,000, and we're setting the master output trigger to be trigo update, which I believe is the correct thing to do. And then over in the ADC init, or is it ADC underscore init? It is. Oh, how do you do next? Oh, that. Okay. So what is it doing? Oh, sugar, I've pushed the wrong button. Okay, here's the ADC in it. So we are saying that we are triggering on timer 2, sorry, trigger out. So that's basically, we've wired timer 2 internal to the chip to the ADC. So it will trigger a conversion. It will do 7 conversions. And here they are, channel 0, 1, 2, 3, 4, 5, 6. With different sample times for the last 3. And it actually generates like quite dense code, which I quite like. Let's see. Now, we actually need to, like the timer, we actually need to start the timer and the ADC. So let me just consider what I want to do here. So, go up to where we're dumping our code. That was the LED stuff. Right, so we're going to have a little buffer of 7 pins times 8 samples. So I'm going to take 8 samples. I'm going to later on, I could use that to do smoothing or oversampling by hand in software. I'm going to take 16 bits at a time. And there are magical weakly bound functions where if you write them in your code, they take over from the default, which does nothing. And we can just set a breakpoint here to prove to ourselves that the thing is removal breakpoint. Oh, we don't have any breakpoints. So we'll put a breakpoint on conversion complete callback just to see that the ADC is actually converting, if you like. And we can then look and see in the ADC buff that it's filling in with magical data. And then the only last thing we need to do is actually kick the bastard off. So it just involves calling basically HAL ADC start DMA. I've got one that I did before. So we start off the timer because we need it to be, and we start the DMA. Let's do it before we start the timer. So basically we're saying start the ADC, DMA, and it won't actually do anything until it gets poked. And we're going to write into the ADC buff, and we're going to write 7 times 8 values. And the DMA is set up as half words, so ignore this typecast. What matters is what you've configured the DMA to in the GUI thingy. And then we hit build. If we're extremely lucky, we will get a breakpoint in the ADC complete callback. And it will have, let's just set the pots to some random values. I think they probably are fairly random. Okay, compiled first time. It's going to work, right? Debugging. Wait for it to go to HAL init because otherwise it will get confused. Hit play. Oh my God, we have a conversion complete callback. Let's look at our ADC buff, it was called. ADC buff over in the watch window. Look, so the values are 0 to 0 to 4096. And those look like 0 to 4096-ish values. So it's working, people. To prove it, let's use our UART. We haven't used our UART for very much, so let's go for int I is 0 to 7, debug log percent, that'll do, ADC buff I, we'll just take the first one, sorry, the 7 channels, and then at the end, we will we'll rewind the line, and we will stop, and we will compile. And then we will twiddle knobs and look in PuTTY and see whether or not it's updating. That's what the chat says. 7 ADC channels. Yeah, three knobs and 4 inputs. Yes. So it looks like the ST chip is so configurable that you could take your ST pins to a header and also make your circuitry to another header. Yes, and indeed, Cutlasses on Twitter has recently done that. So I sort of started my STM journey along with him. He's maybe a project behind me, and he's designed a really neat board that does exactly that. He's made an STM backboard for himself, and he's going to plug it into different front boards. But in fact, the Nucleo is that, right? So this little Nucleo board, I can't see OBS anymore. So this little whiteboard here, which I'm not using except for a programmer, they break out every single pin, all 64 pins of your STM chip, right? So the best thing to do is actually just to get a Nucleo for like 10 quid. They vary in price. I always say less than 20, 10, 7, I don't know, they're not much. Some of them are as cheap as 7. And then just basically you muck around in the cube ID like I'm doing today, and then your pins just work. And what I love about it is that the transition to a PCB is then so simple because the chip basically needs a bunch of capacitors to decouple it and a reset button, and well, that's it. As you've seen in the schematic, it's like this jumper is a panic jumper, which you probably don't have to use. This is the boot. Well, that's part of the panic switch. This is the reset capacitor. These are the stabilization capacitors, a crystal, and then everything else is just completely could be on headers, a couple of caps. So yeah, that's what I love about it. You know, there's a smoother transition to a custom board than from something like a didnt where you have to have the flash ROM on a separate ROM. Anyway, I think it's great. Should we see if the ADC? I'm starting to gabble. What did we do? Let's hit run. Did I compile it? I can't even remember. Let's hit run. Oh yes, I was printing out IADC values. So basically, I'll bring up PuTTY, and I don't know if I can zoom PuTTY. Might be a bit small. Where are you, PuTTY? What? Oh, we've got a breakpoint. Stop being a breakpoint. Start running. Look. Now, if I twiddle, the last 3 should be the knobs. Ooh. That's interesting. We have buggered something up. Why aren't those numbers changing? I wonder. So we're not getting the callback anymore. I wonder if we need to say, well, this is where it's convenient to have a preview. Here's one I made earlier. Let's go and look at the ADC setup on Wagyu 1, which I know works. It's a real stream, people. And I am a noob at this. ADC 1 on Wagyu 1, I have it set. The DMA is set to circular with a FIFO, interestingly. So that's a difference. And I did prescaler. Oh, what did I do? DMA continuous requests enabled. I think we should try that. Oh, the spin cycle on my washing has started. You probably hear that. That DMA continuous. Oh, that's Wagyu 1. Yeah, I don't want Wagyu 1. Go away, Wagyu 1. I want Wagyu 2. Let's set DMA continuous requests. I'm surprised because we're not using continuous requests, but maybe this is the reason. La la la. This is the bad side of it. If it doesn't work, you're basically just like fiddle around until you find Google samples. Go slowly though. That's my recommendation. So basically, it may seem boring the stream that I'm going, methodically. But if you do all this at once and you configure all your peripherals at once, and then you hit go, unless you're an Eric Brombaugh or somebody who's done this before 10 times, it ain't going to work. So scan conversion is on, continuous conversion is off. Yeah, timer 2 trigger out event. I think that sounds cool. Let's just hit save. See whether it works. Take the bets. Where are we? Spin cycle with an Alex voice envelope follower. Yeah, I think this is maybe for a while. I don't know. Spin cycle was not planned. Sucks. Well, let's see if let's ignore that suckage and see whether we've fixed our other suckage. Kind of depressed at it. Oh, it's compiling all. Is it gonna work, motherfucker? I actually sing like this at work as well. My poor colleagues. Right, play. Yes, I got a breakpoint. What? That doesn't look healthy. Whoa. Where did my... Did I type it in the wrong bit of the... Oh, I typed down my printing out. Oh, I typed my printing out in the wrong bit of the... Oh, noob error. Seriously. I must have typed it. Look, the user code is not here. This is no man's land. Thanks, world. Well, let's just print out the last. Let's just be lazy. Debug log, %d, r, ADC buff, 5, 6, and 6. 4, 5, and 6. The last 3, which is the knobs. Don't care about the other ones. Stop. Stream goes wrong. I said I had another 40 minutes to go. We can do it, Evans. Will it work? Come on, puppy. Ooh, and look, the numbers are changing. Success, right. This knob is the last number, so the bottom knob, which is the rightmost on your screen. Can I make this bigger? Does Putty do embiggen? How do you do full screen? I bet you it won't actually make it bigger though. I bet you it'll just be like, change settings. Christ. Appearance. Change. In massive innate. 20. Yes. Apply. Look at that. Science. So that number goes to 4095 when it's all the way up, and twiddle it all the way down. I'm not clearing the end of the line, but I promise you that's 1. And then if we look at the middle number, that's the middle knob. Oh no, the middle knob is the first number. Interesting, I wired up the wires in a weird order. So that's the first one I'm changing, which is the middle knob. And this one is the bottom knob. So we have successfully hooked up 7 ADC pins, including the last 3 of which we were sending to the TTY, which I think is a big success. Let's use it to animate our display a little bit more excitingly. So that VRAM buffer that I created ages ago, when we can get rid of our in our interrupt, sorry, in our callback called update LEDs, I've got the thing that's basically slowing it down. So we can sod that off. Right. So reminder, it's reading from this buffer VRAM, but we've never written to it. So let's write to it. We don't need none of this stinking TTY anymore. We need basically shader coding time. I'm not going to copy paste this. I'm going to code this and talk through my thinking. So basically, I'm going to write a shader toy on an 8x8 grid of LEDs because that's how I roll. So basically, let's say that we want the 6, which is the top knob, and I noticed that it was backwards. So let's make it not be backwards. As in, 0 was all the way up and 4095 was all the way down. And that was just the way the board layout came. So live coding time, that actually feels good, right? XY radius, we're going to draw that little blob. We want that to be backwards as well. And maybe not 0 size blobs, that's radius. And we're going to square the radius because we want Pythagoras times, Jesus. Right, now we're going to loop over our pixels. Let's do X. Oh, we should do Y. Let's do Y. Okay. We can pull out the Pythagoras term, right? So basically, we're going to say in the scaled, the knob is 0 to 496, whereas my pixels are 0 to 8. So the pixel center in a 4096 4K by 4K screen would be times 512 plus 256. That's the Y1 is the coordinate of the center of this pixel only in the Y things. And dy is going to be the difference between the center of my knob as set by the Y0, which is the position of the knob, and this pixel. So I'm basically going to compute the distance of this pixel from the dot which is set by the knobs. So the knobs are setting an X and Y coordinate on my virtual 4K by 4K screen. And then for each of the 8x8 LEDs, I'm going to figure out the distance to that point and then light them up brighter when they're closer. And that gives me a little soft ball. It's not quite a dancing equalizer, but it's close enough. So that's Y. Let's do the X loop. And plus I'm a graphics programmer by trade. So, if I can get it down to a pixel shader, which is basically what this is, then, same sort of deal. All right, so let's do a Gaussian. So we're going to have a color, a Danish color starts with K. E to the minus distance squared, right, guys? So this dx, dy, let's square them. Let's pre-square them. dy times equals dy. Pythagoras. Dx times equals dx. So we've got dx squared plus dy squared times by e to the minus, let's divide through by the radius. Okay, so that's a Gaussian fall off. So that's basically a Gaussian blob with radius r0, which we have pre-squared, so everything's squared, which is good. And then we're going to just set it. VRAM y x equals, now they're back to front, so 255 minus, because 0 is bright and 255 is dark. We want it the other way around. So that, and this is a gamma curve. So basically, here is our linear pixel brightness. 0 is black, 255 is bright, and then it's like flip it because I got the pins backwards, and the positive and negative pins backwards because I'm an idiot, and square for basically a gamma curve. It's not gamma, but it's like the perceived intensity is of your eye. You should do that. Right, so we're filling in VRAM with some stuff. So I don't know whether it will compile first time. Take your bets, 3, 2, 1. Spot the typos. How many typos? Unused variable I. None. No typos. Where's that? Oh, yeah. That was what we were using as our callback to check that I don't like warnings. Kill. Check the ADC was running. Let's see how the chat are doing. I really like large blob. You normally see it being lit. Looks like it has a slight wobble thanks to the analog nature of the sample. Has life to it. Yes, I agree with you, Mike Ball. I appreciate your appreciation because I feel the same way. It compiled. Holy moly, people! So we've sped up the muck, so it should just turn back into a coherent blob. And then we hit play. Oh, hang on. Oh, there it is. Y, X, bigger, smaller. Look at that. Look at that, people. Sub-pixel accuracy. That is creamy. I mean, I don't know if you can see that, but that just looks so damn creamy. It doesn't look like it's running on an 8x8. It's anti-aliased, people. That is, properly band limited Gaussian. I'm just going to appreciate that for a moment. Yummy. Okay. We have done knobs. We have done LEDs. Now we're going to showboat a little bit. We're going to do CV inputs because it's almost no code change. What we are going to do is actually, I'm just going to. Should we go full screen for a moment? Overhead cam. There you go. So this is radius, all the way down to less than a pixel. Whoop. And then this is X. Wee, so lovely. And it doesn't actually come out on the camera as well as it does in real life. In real life, it's a bit dimmer and it looks like a proper sort of super smooth gradient. But as Mike points out, there's a bit of life to it because it's just raw, oversampled ADC values. So we're getting a bit of jitter to it. Anyway, it's yummy. But now instead of driving it by the knobs, or we could drive it by the knobs plus the. Let's drive it by the knobs plus the Jiminy Whatsits. Switch back to the code. Analog inputs. Right. So that's as simple as where I set the X and Y. I'm going to add on ADC buff. I don't know, 0-ish. No, let's go for 2 because 0 and 1 are aliased against the audio inputs. So let's do 2 and 3, and it rests around 2048. So if I take off 2048, so now we're basically reading not only the pots, but we're adding on the CV input. We say stop. We say compile, and I don't know if you've noticed, but we've actually got a pretty functional module now. We've got, it doesn't make noise, but we're about to have CV inputs. We've got displays, we've got knobs. I mean, that's half the battle, isn't it? So they tell me. Debug. I will do the encoder because it's really quick and it's an input, and we haven't done inputs, and I can show you how to do pull-ups. Not the exercise kind of pull-up. Anyway, hit play. We should still have the little blob movable roundable. Yes, we do. All right, let's go to overhead. Shit. We're going to pull out the ULD analog discovery, and we're going to use this wave generation, like LFO basically. Got 2 of them. And I believe that the ADC channels that I selected were the B and C inputs. So plug that bad boy in. Oh my God. Cables everywhere. Short out something. Right. What could possibly go wrong? Hoink. Waveforms. I like this program. It's cool. Waveform generator, sine wave. I don't think we'll be able to see 1 kilohertz. Should we go for 1 hertz? Amplitude 5 volts. Yes, please. Run. Oh my God. Look, it's waggling. Stop. Let's have another channel. Boom. Let's go for 1.3 hertz. This is the Didnt Analog Discovery 2, which can simultaneously do 2 channels of signal generation and hey, listen to you figure. Demo scene confirmed. Revision's running at the moment. If any of you are into demo scene, I recommend the revision stream. Shout out revision crew. We now have a single shade bulb running on a 8x8 display. Wild competition is happening on my stream. And we are driving its position both by the knobs, which I can basically scroll it, offset it in the X and Y, and I can set the radius still, little, big. And it's being, waggled by the, what shapes do they do? Noise. Go on then. Is that, oh, it jumps every sort of second or so. 10 hertz. Okay, I'm just having fun now. Stop. Right, CV input's confirmed. And so I guess square the circle, something. The entire circuit for that is here, which is basically jack, 100K input impedance, 3 to 1, minus 1/3 basically gain, and an offset from a 5 volt reference, or minus 5 volt reference, I should say, that basically centers it in the output range. So joy. Right, the CV input's done. Let's do the encoder, because that's easy. I have forgotten what pin the encoder's on. Here it is, up, down, and switch. And it allows me to show you pin interrupts as well. So switch we're just going to do as a standard input, and up and down. So 2 and 3 are going to be interrupts. Oh, right then, easy. Pin 2. Let's stop the debugger so we get a bit more screen. Pin 2 is going to be a external interrupt. I mean, seriously, who chose that? XD14, do not panic, that's the external interrupt. And then pin 4, which is the switch, it's just an input. Now, you think you're done, but you're not. You need to go to the GPIO section. And those are PC 13, 14, and 15. And basically, we need external interrupt for both rising and falling. Otherwise, we're going to only trigger on, so an encoder is basically 2 switches 90 degrees out of phase. And as you twist the knob, they make square waves out of phase with each other. And you want to get the chip to get called back every time they change up or down. So rising / falling. And if you look in my circuit, I just connect the naked switch. Where are you, switch? To ground. So the physical switch connected to ground, but there's nothing pulling it up. That's okay. We can stick a pull up in, and they do pull downs as well. So good. And this one, likewise, rising, falling, with the pull up. This one, we want input with the pull up. Excellent. We hit save. And then we go and write a little bit of code. I think I'm going to do this copy paste style because time is short. All right, done the LEDs, done the ADC, that was easy. See, and we haven't even used any. So something I like about this is that I found the Teensy ecosystem was amazing in terms of the fact that you can get a library for anything, which suits some people. But I tend to like to read the source code of everything. So every library I add basically adds overhead because I need to understand how every library works. So I prefer the HAL. I hate the HAL. I'm going to get rid of the HAL. In some future stream, I'll mock myself from this stream and say, like, lol, that you were using the HAL. But actually, for this, I'm not going to use the HAL. So, haha. Future me, in your face. So all I've slapped in here is this is our encoder callback thingy. Basically, every time a pin changes, it tells us which pin, but I'm going to ignore it, and calls us back. And then I just wrap that into a nicer function called update encoder. And you have to call it this because that's what the linker expects. So then update encoder basically reads the GPIO-C, which is the pin, input data register, which is all 16 pins at once. And then we used 13, 14, and 15. So we shift it down 13 and mask out the bottom 2 bits. That's basically 13 and 14 are now sitting in bits 0 and 1. Then we decide whether or not it's changed compared to the previous one, which it will have by definition because we just got a callback. But regardless, I just do a check, why not? And then we basically say, fine, if it's changed, then the change in the value is basically the XOR of the lower bit XORed with the previous higher bit. So you've got 2 bits. And basically, I'm only interested in the higher bit position. So the higher bit position from the previous frame, previous sample, and the lower bit shifted up into the higher bit of this sample. And basically, that circuit is the classic. You can do an encoder. In an FPGA, you do this with a single XOR, basically. And so this is our XOR gate. This is our wiring. If I was doing this in FPGA, it's easy. That gives us a value of either 0 or 2. And then I subtract 1 to make it plus or minus 1. And then we increment our encoder, and we remember the previous value. So that's our encoder logic. And then we update something called enc_val. So let us initialize this a little bit by calling update encoder once, just to prime the pump. And let's go back to using our debug log magic to show the encoder enc_val and spot all the typos. Will it work? How's the stream doing? Wink, wink, wink. Is anyone still here? Okay. Yes, you are still with me. Amazing. Hilgeran? Will it work? I mean, I copy-pasted it from one that did, but that's no guarantee in hardware land. I'm starting to go mad. It's that time of night. Pumpkins, nearly. 3, 2, 1. Run. Putty. Take me to putty. 0. That's encouraging. So an encoder is, let's go full, I can't go full screen because you're looking at putty. So basically, oh, sad times. Mother of God. Should we see if we're getting a breakpoint? Ah, actually, this is a really good learning moment. So this is like, it's not happening. So you curse and you cry, and then you think, well, I need an interrupt to happen. Shall we go and look at the interrupt controller? And shall we go to the XD line interrupts, which are conveniently added for me, knowing that I would need them? And then it didn't generate the interrupt handler. Why, thank you, ST. That was mighty kind of you. So merely clicking that box will now generate the actual interrupt handler, which will call the callback, which will then call the update encoder, which will then actually do the work. That's another top tip from this stream. You see, watching this stream, if you're bringing something up, you'll be like, oh, you see, Evan's made all the mistakes for me, so I don't have to dig around it. Finding that screen was the right one to click on because it'd forgotten to tick that sodding checkbox took me the first time a bunch of time. I'm not bitter. Debug. Okay, take your bets, people. Second time lucky. Take me to hell in it. Oh, draw your screen twice. You can do it. Hit play. When this stuff runs this slowly, you can kind of see all the hilarious. Oh, I got a breakpoint. Indeed, I twiddled the knob and I got a breakpoint. 1. Woo! So I'm turning it right and the number goes up. I'm turning it left and the number goes down. And because we had a breakpoint, we're actually offset by 1. Normally these are like round multiples of 4, because basically it generates 4 edges per click. You can even hear it clicking probably. This ASMR. Wow. We're not actually reading the button yet. I feel like for completeness we ought to do something with the button. What I did before was I made it invert the display. Should I just do that? I'm gonna make it. I'll do what I did before. I'm gonna stay shockingly on script. So basically, let's light up 1 pixel, So if x plus y times 8, in other words, the pixel number, is equal to the encoder value divided by 4 because it goes up in steps of 4, let's say it's bright. And then also, let's say if GPIOC input data register shifted right by, what pin did I use? Switch PC15, ANDed with 1. So if the switch, if you're clicking the button down, physically pushing it down, we'll flip the color because we can. That takes me to parity with my original plan. I mean, we might even get to codec. We are going to get to codec because it's the only thing left on this entire device. I might do a Q&A for 5 minutes. Prepare your questions once this encoder works gloriously well. Hit play. Let's go full screen. Oh, look at that! It's permanently inverted. And then when you can't see. When I pushed the button. All right, so I'll talk about why that is in a moment. But yeah, so now the button will invert it when I press it down, and then also I can, as I wibble the encoder, I can select different pixels. So why is that back to front? Easy, because the circuit is back to front. Well, the circuit is classic. It's that the switch physically pulls it down when you press the button. So the input bit is 0 when you're pressing it down. So I'm a duh, so I just stick a not in there. I hope you have pithy questions for me. To recap, we have gone from a board, a design of which I did on my last stream. Well, I didn't really do the design, but I sort of covered how the design was done, the meta design. It was sent off. This is an unpopulated board. JLC PCB delivered me. I only asked for 2. I should have gone for 5 because this actually works, but I wasn't very confident because I hadn't really thought it through. So they delivered 2 of these manufactured. It was like $7 overhead plus $15 because I chose weird parts plus bugger all. Amazing, really. We soldered the knobs and things on in time lapse, stuck the front panel on, also made by JLC PCB. And over the last hour and 40 minutes, we have written enough software to do CV inputs, knobs, buttons, encoders. The only thing missing is the audio rate inputs and the audio rate outputs, which I will get a sine wave going. And then on the next stream, we will write some audio. And I'll also talk briefly about I2C bit banging. And then it'll be probably midnight my time, and I will pack it in 2-hour mark. Let's fix our backwards black and white bug. Stretch. I should have got a bigger teacup. Okay, will it be back to front? It won't be because perfection. So I can select the pixel, I can flip it with the button, and I can move it around as ever with the knobbies. Lush is what I say to that. Okay, brief pause, and then we're going to do I2C bit banging in order to bring up the codec and make a sine wave. And I will then bitch about another bug that I found in HAL, how to work around it, for which I have not found as good a workaround on the internet. So this will be world first. And then I shall go to bed. We win Demising, we have a tunnel. Right, any questions, anyone? Nobody has any questions. You're all in a coma. You're all watching Netflix, and you're all sweet, lovely people. And you've left it on your YouTube in the background so that I feel like I have someone I'm talking to. I'm not going mad in my coronavirus thing. All right. Codec. So mostly this is going to be chat. I'm not going to live code a codec because codecs are just horrible. There's something I want to use actually. Is a didnt have, I need to switch back. Noob error number 2, switch back to desktop with cam. Google, the Googles. Oh, hang on. I'm curious about the utility of the screen. Oh, Eric, you're still here. Ray, you're still here. Mike, you 3 are heroes, and Jonathan, thank you. You 4 have kept me going. Rich in Paradise, everybody, shout out. Well done. Utility of the screen. I'm basically going to use the encoder to select presets. Kind of maybe it's a bit like a kind of my own personal disting, if you know that module, sort of multifunction module. So I was planning to basically just make it so that I turn the encoder to pick a thing, and I'm just going to draw an 8x8 little image of the different presets. So I have like a monkey, or it'll take me back to my ZX Spectrum days. And so each preset will just have a silly character, and then I'll do an animation, a bit like the pocket operator on the 8x8 display, based on what the effect is, or the patch, if you like. So it only needs to be able to convey, I think, what the module's doing at a glance. And then you've got three parameters that you control by CVs, same three parameters by knobs. Well, actually, they could be separate. So three knob parameters, three CV parameters. Maybe you can convey some of that on the display. But I don't want it to be a computer display. I want it to be a module display. So I think it's a nice sweet spot. And I have been building things with OLED displays, but I'm actually enjoying this one way more than the OLED displays that I've built. So, shrug. I've managed to choose the view without the overhead, but not that you need the overhead, but I feel like it needs to be there because it's pretty. Right. So yeah, Digilent have this PMod I2S board. I think it's this one. And they basically use a separate chip for the input and the output. So I don't know if there's so basically there's this little chip here which basically does serial audio over I2S format, which is what we're going to use into analog stereo out, and then another one for doing in. And the advantage of these two chips, which I've never used, is you don't have to configure them. They just work, which I love. Unfortunately, the most codecs, the one I'm using is in fact, I shall tear off a page and bring it up here. So I'm using this codec because it has a headphone driver and because JLC stock it. And I'm not using the headphone driver on this board, but on the Plinky, I wanted a headphone out. So it's this thing is a beast. So basically it has, I hate this data sheet as well, has the most ridiculous signal chain. And I happen to know, having lived inside this data sheet for too long, this isn't the one that everyone uses. Everyone uses WM8751, which is a bit simpler. This is a later chip and a smaller footprint. It's QFN. It has all of these like registers, and you basically have to set them up over ITC to make the fucker work. And it's really dark because if you don't get them exactly right, it just doesn't do anything. So you have a dead chip, and you don't know if it's your circuit, or is it the HAL bugs, or is it the DMA that you got wrong in the configuration screens that we've been going through today, or is it any of these registers that you've got to set, and they're all scattered. These are bits, so you have to set every single one of these correctly, which I did on your behalf yesterday afternoon. So I will now use this amazing program I have called Windows Explorer. Not my Dropbox. Dev. Oh shit! I can't remember where I put it. I think it's in users, mmalex, STM, workspace, MagU1. Right, this file I'm just going to steal because it's too boring to write. I will briefly show you its contents and talk about it. So I'll paste that in there, and then we come back up to here and we just include it down here, #include codec.h. And then via the magic of computers, we can call, what do I call the function? I don't remember what I called the function. Codec. Yes, I called the function. What did I call the function? Ah, yes. Okay, so what I'm going to do, I'm actually going to do a little bit of, after we've initialized everything, we are going to make some buffers. We're going to do this line and not that line, and I will talk about fix st shit in a moment. So the idea here is we're going to fill a buffer, transmit buffer, with a sine wave, and it's actually a stereo buffer, but I'm basically just filling this both. It's left, right, left, right, left, right, left, right. So they're basically just be sine wave, one big sine wave, and this is how I bring up all codecs. And I'm going to have 64 samples times 4, so I'm basically going to be stereo double buffered blocks of 64. So n is going to be 64. And we're going to basically fill in so that's stereo, so that's 128, double buffer 256. So we're going to fill in a 256 sample sine wave. And then we're going to call transmit DMA, which basically just says, please send this over I2S. So in order to do this, we have to configure the I2S pins, which I happen to know are over here. So you have the word sync, which is basically let me see which, they all have different names, so I'm just going to configure them all. I2S data and I2S master clock. So we're going to configure this to spit out a master clock, which basically runs the codec at whatever megahertz it is. Then you have the data, which is basically please play this audio one bit at a time. This is basically an abused SPI peripheral. And actually, good tip, if you're bringing up an SCM chip, the newer ones use a peripheral called an SAI, which is a serial audio interface. And they typically have 2 or 3 of them. And each one has an A half and a B half. And you can use, therefore you get 6, basically. And it's super flexible, and it can do TDM and I2S and all these different formats. And you can configure them half duplex, full duplex, blah, blah, blah. And it's all very modern and very lovely. But in the olden days of the STM32F405, they'd only invented the much less flexible I2S peripheral in the hardware, which is actually the SPI peripheral, serial data peripheral, with a couple of extra knobs and clocking options. So this is the input data. So it's rather suspiciously on the same pin as SPI2 MISO, because that is exactly what it's actually using. It's actually using the SPI2 peripheral, master in, slave out. And then you have a bunch of clocks, basically. You've got the, I think that's the bit clock. And then this is the left-right clock. So basically, it alternates between the left channel and the right channel. And then we go over to multimedia, and we say I2S, full duplex master with master clock. And that uses up all our pins. That's basically all we need to do. Oh, we need to set up the audio, right? So parameter settings, let's have a look. I2S Philips, 16 bits. We could do 8 kilohertz. Let's do 32 at least. And that's all fine. Let's have some DMA action. We'll need some DMA. Have I got the streaming right? Yes. Are the stream shouting at me? 5 pins for audio, yes. In and out stereo, serial. Right. So we are going to have the transmit DMA, and we'll have it in circular mode. And we will not use the FIFO, and we will transmit half a word at a time. So that's our transmit side. So that's like us transmitting audio. And then we also want a receive. And we would like that also to be circular, obviously, and we would like that to be 16-bit at a time, and that is all good. This codec actually does 24-bit, so we could actually send 32 bits, and it takes the top 24. But I'm not going to bother for now. 16 is fine, for good enough for me. Right, so we've set up the DMA, set up the parameters. We have got all the code. We hit save. And it takes its sweet time. We're calling transmit DMA, and we're saying txbuff. Okay, so I have to declare txbuff, otherwise it's not going to compile. So let's see how big a txbuff I want. I would say I would like. I'm going to take. Yeah, let's do that. Okay, so where do we declare the VRAM? So we've got buffers of 64, and we need 4 times as many because we've got double buffer. And the way ST work, it's really nice actually. They call you back halfway through and at the end. So basically you have 1 buffer, but it behaves as a double buffer because you get a callback. I wonder if I have TX complete callback. I haven't, I can't remember, but basically you declare something equivalent to this. I think it's like void, let's try S2I DMA complete callback. And then you get Does that exist? I think it does. Let's try Googling it. Let's try Googling it. Oh, let's Google it in a window that you can see. No. Oh, sad times. Luckily, I downloaded earlier the user manual. So I can do how I2S, yes. What do we reckon? DMA? No. Oh, sad times. Transfer complete. What? Okay. This 1800-page document is not helping me out. Let's go for the I2S driver. So we go la la la. This is useful as well. This is how you find out how to do this stuff with the HAL. So you find the driver you want, which is I2S, not I2C. And we say la la la. How to use this driver? You call transmit, and it will call you back. I hope. Yes, tell me. Aha, there you go. TX half complete and TX complete. So if we paste that back into our code, how wrongly did I spell it? S2I, I2S. I'm tired. Let's find the definition of that. Come on. Yes. Yes. Oh, it just takes a I2S. Jolly good. And we will set a breakpoint there. And they have a half complete one as well, which is a really nice one. TX half complete. And we'll put a breakpoint. Let's remove all the other breakpoints. We don't have any breakpoints. Okay, we're going to peek, and hit compile. So, recap. There's a bunch of things you have to get going for a codec. You have to start sending it data, which is what we're doing with this transmit DMA. And that's just going to loop round and round and round because we set it to circular. Round and round and round and round and round. TX buff in words because we set it to words, so 16 bits divided by 2. And every time it's completed that full buffer, it will call us back here. And when it's got halfway through the buffer, it will call us here, which is exactly what you need to fill it in with audio, which is how we fill it in with audio. However, I have also pre-filled the buffer with a sine wave. Then, having got that puppy running, you then call codec init, which I haven't shown you, which is I2C stuff, which basically configures all of the registers in that chip. And if you've done everything completely perfectly, it will produce a sine wave. And basically, if you can produce a sine wave out of that, then you're happy. So we will move these to be the output pins. Yep. And then we plug them into the scope rather than the signal generator. We hit play. Aha, look, we have a breakpoint in half complete. We have a breakpoint in completely complete. And we hit play. And then we come over to waveforms with only 2 minutes to go on the clock. We don't need wave generator anymore. We need scope. Should we just hit run? Ha ha! Look at that. That's the sine wave, people. A beautiful, clean pair of sine waves. Not offset. 2 volts per division. So there's plus minus 4 volts. It's good for audio, I think. I mean, maybe I could have made it hotter by changing resistor, but for audio, I think that's all right. Maybe any eurorack people in the chat can tell me whether or not that's too quiet or not. Is that full scale? I don't even think that's full scale, actually. I think that might be... What did I fill in my sine wave? Let's go full scale. Let's try it. So I filled it in with... I didn't go all the way. 32767's all the way. Let's see what full scale is. Compile. So yeah, so we've pre-filled a buffer and we're not actually filling it on the fly. We've just filled it once on boot. And the reason they are very slightly out of phase with each other, if you noticed, the blue line is just behind the yellow line. I don't know if you can see that on the stream. It is. So it's just debugging. Wait for it. 3, 2, 1, go. Okay, that's full scale. Plus minus 8 volts. That's quite juicy. So basically, if you remember, I'm filling in a single buffer and it's left, right, left, right, left, right, but I just wrote it lazily as a single sine wave. So basically, the left channel is one sample ahead of the right channel. Now we set it to 32 kilohertz, and it's a 128 sample dB. What's it? 32,000 samples a second divided by 128. So it's about 250 hertz. Should we have a look? Measurements. Add. Define measurement. Channel 1. Horizontal. Frequency. Oh, look at that. 254 hertz. So that is the codec functioning. And I'm just going to wrap up my entire stream by saying to do receiving, you basically call this function. And my rage is manifold. First of all, this function is not in any of the samples. So this is hardly documented. And it's in a different library. It's not in the I2S library. It's in the I2SEX library, which probably makes sense to the people in ST. And the people who wrote this library are different from the people who wrote that library, because the people who wrote this library decided at some point about 2 years ago to change their behavior and not bother calling you with a complete callback. So they, we rely on these complete and half complete to know when each buffer is finished, but they don't call you back. And if you go and read the source code, it turns out that they don't do it because it's circular. So they only call you for the half complete halfway through the circle. But at the end, they get the IRQ, and then inside the HAL code, they just go, it's circular. You probably didn't want to know about that. Fuck it. And they just drop it on the floor. So what you need, and the other thing that they do, just to make your life even worse, is they call the same callback, which is called TXRX complete, for both transmit and receive. But they don't tell you which is which. So you basically get two callbacks for each. You get complete, complete, half, half, complete, complete, half, half, which is just bullshit. So the most elegant fix is that you replace their 4 callbacks directly with your own, and that removes one layer of indirection, and it removes their bug, and it removes the double call, and you can then do full duplex, by which I mean you can record and transmit at the same time. But because it's a little bit late, I was going to demo basically recording and then sending that back out, so it's basically a wire, and then maybe I was going to do DSP, but we're close enough. We've got knobs, 8x8 LEDs, encoders, CV inputs, and analog output at audio rate. And you'll have to trust me that if you do this transmit receive DMA, you also get audio rate input on 2 of the pins. So I think that is actually, I'm going to call that a success. A little bit longer than I'd hoped, and I didn't get quite as much done as I'd hoped. But I'm just going to move that into a whole DSP stream in a week or two. I hope you enjoyed that. Let's go and have a look at the chat. See what they are saying. Let's go to overhead cam and who are their chat? I don't even know anymore. It's in a Chrome window somewhere and it's scrolled off the bottom. And I just don't know. Here you are, YouTube. Don't use the WM8731 codec. Well, I didn't. That's lucky. Pro tip. Thank you, Eric. Pro tip for anyone listening. Don't use the WM8731 codec. Its audio input is super noisy. And he's also coding up a Raycaster on the STM32 G431. Very cool. Low power chip, I believe the Gs are. Yeah, I should do a Raycaster on my 8x8 display, shouldn't I? Oh, the ITC. Yes, I will show you the ITC right now. Typical Euro oscillators run at plus minus 5 volts. Okay, so I've gone for 8, which means I could use this as a CV thing, except for the fact that I AC coupled it. Let's have a quick look at the output stage. It's currently AC coupled, but I could drop that capacitor and then I could bias this by V mid. So basically this thing has a mid output, I believe, yeah, V mid. Or maybe you can configure one of the other outputs as a mid-scale reference. And then basically you can use that as a reference on the input to an op-amp to bias the, I don't know if that's a good idea or not, maybe Eric can tell me, to basically do a differential output between the mid-scale, midpoint and the thing. Then I could do DC coupled, assuming they haven't stuck a digital filter into the codec. Anyway, this is great. I don't have Windows No, you can use Cube on Mac, and it works fine. And I believe on Linux as well. I've tried it on Mac. Um, and the VS Code tooling, there is VS Code tooling in the sense that you can use generic Cortex M4 plugin, apparently. And if you search for like STM32 Visual Studio Code, there's a bunch of people who've written Python scripts and stuff to make it less painful to set up. But as far as I can tell, it's just basically software wrangling for a few hours, and then you can use it. Right, let's look at the I2C, and then I really will wrap it up. So there's actually a really good diagram in the sodding Microsoft Word doc. And scroll until I see timing diagrams. Oh, no, that's not the one. I think it's called 2-wire. They had a nice diagram of the I2C. Oh, here you go, this one. Oh, I better go back to my desktop. Third time I've done that. So this is what I2C looks like. Basically, to talk to the codec, you need to bring the data low while clock is high. And again, I could have used the HAL I2C library if I hadn't missed off the sodding pull-ups. So you pull this low, that's called a start condition. You then feed it 7 bits, which it documents only in binary in this data sheet. So if you search for device address, you have to know that it's in binary. Thanks, guys. 7-bit address. Then you can only write to it, so that's always 0. Then if you've got the right address, the chip, the codec, pulls the line down. So basically, the annoying thing is this is an output because we're the only master. So we can just set clock as the master. Oh, you know what? Oh yeah, I didn't actually configure. We were very lucky. I didn't actually configure the SDA and SCL pins in here, so they're actually unconfigured, but they must have just worked for reasons. That's hilarious. What pins were they? 61 and 62, which I think is up here. 50, yeah. So this one I needed to configure as a GPIO output, and this one also is a GPIO output. And I basically set them up as outputs, defaulting high. Is what I should have done. I didn't bother, but I set them up as outputs, and then annoyingly for this ACK, you basically need to switch the data line to a read, and then I actually set them up as open drain outputs so that they can only pull it down, and then I use an internal pull up of the chip so that I'm not fighting the codec. So I skipped that bit, but basically you configure the SDA line as a output open drain only with a pull up resistor, which is 20K, which is too high, but then we're going to do it really slowly. And then basically I just wrote by hand this timing diagram. So I basically sat and looked at this exact timing diagram, and then I wrote some code to do it, which is here under codec.h. Now I Googled and I found bitbound I2C. So I wrote myself, this sets it SCL to 1, SDA to 1, SDA to input, SCL to 0, SDA to 0. And they basically set output data register and mode, which is why this worked without me configuring it through the HAL, luckily. So basically this is just saying be an output, B1 for clock and data. This is saying be an input, and I think I've set it high. I don't think this is used when you're an input, but I do it anyway, superstition. And this is be an output low, be an output low. And then this is a short delay, which is like meant to be a microsecond in real I2C. So I just loop a bit and increment a volatile to sort of optimize it from optimizing it out. And then read SDA just reads the bit 9, which we set up as an input. So then basically, the way that you write is that this implements that diagram, right? So I sat with this diagram and I just do data goes down, wait a bit, clock goes down, wait a bit. Now this is the 24 bits we're going to send. We send the address, followed by the 9-bit register, followed by the 7-bit register, followed by the 9-bit data. And there are a bunch of, if you read other people's libraries, they have to do this by bytes. But because I'm bit banging it, I'm just like fuck it, I'm going to put the whole 24-bit transaction, this whole diagram, into a single shift register, basically 32-bit shift register. And then I'm going to loop over 3 bytes, and I'm going to basically clock out the bit high or low, MSB first. So that's the MSB of my 24-bit value. Short delay, clock high, short delay, clock low, shift it up towards the MSB. So for the next one, do 8 of them. Then I switch to an input, short delay, clock it, short delay. The codec replies and says, yes, I'm happy, by pulling that low. So ACK should be 0. If ACK is ever high, there's a problem, the chip's dead or something. And then clock 0, so finish the clocking out, do it 3 times for 3 bytes, and then this is the stop condition. So this is the right-hand side of the diagram. So you basically pull the clock high, wait, pull the data high. So yes, indeed, pull the clock high, wait, pull the data high, done. And then if ACK was ever high, that means the chip didn't reply. That's called a NAC. And we got a NAC, oh no, we got a NAC, and I print it out. And that never appears. We could look in PuTTY actually and see whether or not it showed up in PuTTY. Oh, well, we're printing out our encoder value anyway, so it didn't. And then basically I found all of the constants in that datasheet. Someone had written it out into a GitHub repository, so I stole all of their hash defines of like all the register values. It's basically the datasheet written out in C. And then I spent an hour yesterday setting all the registers to the right values by reading that datasheet very carefully. And so each of these is basically sending that 3 bytes to the codec. And every single one of these values has to be right. And if you're using the 8751, which is one that everyone uses, then you can just go and copy it out of the TNC audio library or somebody else's. But unfortunately, the 87 blah blah, whatever I'm using, 8758, is less common. And I think this is from a project called the Rockbox, which supports loads of codecs. So thank you to the Rockbox project for basically, they follow the data sheet in the end. So I stole all their hash defines, and then I read their initialization, and it's basically a copy paste from the data sheet. So I just followed the data sheet's instructions and then configured it the way I wanted it. So I basically need certain gains. I want certain bits of the chip to be on and off. And so you basically just do this. And what's gross is if you don't get that right, and you don't get the HAL DMA stuff right, and you don't get anything right, and you don't get the wiring right, and you don't get the PCB layout right, you'll just get a dead chip. So it was completely fucking awesome that all the stars aligned apart from my lack of pull-up resistors, and I was able to make the thing run. Right, that was the I2C. Yeah, your bitbang I2C is probably less overall code than using a HAL I2C lab. I agree. I really don't like the I2C libraries. And their API sucks. Like, it doesn't let you do stuff like don't do a stop condition. So you feed it stuff, and it always does a stop condition, and it does it through a nasty tangle of IRQs and stuff. And it's just gross. And so, yeah, I've actually had NACs and intermittent failures on the Plinky board that had pull-ups and used the proper library. And like 1 time in 10, it wouldn't boot properly. And I had to put retries in. And with my bitbang, I've never had it go wrong. And in fact, it just worked without me even configuring the pins, which is hilarious. So blah, 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 blah. I think I better stop. That was awesome. I really enjoyed that. I hope it was instructional. And I hope that anyone in the future who wants to make digital STM-based, I've got hiccups again, emotion. Anyone who wants to make this sort of thing, you can. It's really easy. This is brain off stuff. Like the purpose of the stream is here's the fast path without all of the mistakes I made, or in fact, some of the mistakes I did remake on stream so that you can see how to resolve them. And getting to that point yesterday was 3 hours, and I was lucky because the board worked. And I'd done it once before with this codec with Plinky, and it probably took me 2-3 hour sessions to get it working on Plinky. So basically next time I can just probably copy paste this from my library, and I can copy paste the chip. Maybe I'll put the pull-ups in next time. But yeah, I'm going to stick the code on GitHub, and I'm going to stick the Gerbers and the KiCad files on GitHub as well. I mean, if I ever write some decent DSP for this, and I do have some ideas for a module to turn this into, I may hopefully, make a few and sell a few one day. But in the spirit of, much more brilliant people than me, like Eric and Emily from Musical Instruments, they've put all that stuff online, and still, I have no intention of making a business out of this. So hopefully one day I will sell some of these things to you if you're not interested in making it, once I've put some useful audio stuff on it. But also I'm going to just throw the files up because they're not particularly special, and you can transcribe them from this YouTube stream anyway, so might as well. Yeah. Thank you very much. I've kept you for long enough, and sweet dreams. Stay safe, stay healthy. Don't go out, stay home. And yeah, I hope you all enjoy that, and see you next time for some DSP action, hopefully. Bye. Now, this is an interesting question. Do I just sit here awkwardly until the latency kicks in on YouTube? Or do I don't know. I'm just going to wait until I see myself waving.